Hello, I'm Dave Brown for Teletrain. Today we continue our study of Parker Hannafin's Industrial Pneumatic Technology with Part 1 of Lesson 7, covering check valves and two types of pneumatic actuators, cylinders and motors. Here is an important pneumatic system component. It's called a check valve. It's called a check valve because it allows air to flow in only one direction. You can see that there are only two openings in the valve body, the inlet and the outlet. This arrow indicates in which direction the valve will allow air to flow. Here we can see all of the main parts. This is the valve body, and these are the inlet and outlet ports. The movable part is called a poppet, and it's held in place against this valve seat by this spring. The poppet in many check valves uses a seal made of a resilient material. It assures that the flow is fully stopped or checked when the poppet rests against the valve seat. Right here we should explain a new term. The term is biasing. It means that a force is applied to a moving part to hold it in a certain position. In the case of the check valve, the poppet is biased against the valve seat by the force of the spring. Here's how the check valve works. When the system pressure at the inlet becomes high enough, the force of the air overcomes the force of the spring and any back pressure, and the poppet moves away from the seat. There is now a path for air to flow from the inlet through the valve to the outlet. This is defined as the check valve's free flow direction, and when the pressure at the inlet drops, the poppet is again biased closed against the valve seat. If air attempts to enter through the outlet, the poppet is pressed firmly against the valve seat, blocking airflow through the valve. Here is the symbol used to represent check valves in pneumatic circuit diagrams. Here is a circuit that makes use of a check valve. The application allows free flow around a flow control valve, which otherwise would restrict flow in both directions. In this case, it allows air to enter more quickly into the cylinder, so the cylinder will retract more rapidly. You'll remember back in Lesson 2, we described how a simple pneumatic cylinder works. Well, the cylinder is the most common type of pneumatic actuator you'll find in use. The primary purpose of a cylinder is to convert pneumatic energy into straight-line mechanical energy. Here is a typical pneumatic cylinder. There are two cylinder ports here and here. And this rod is attached to the piston inside the cylinder. This end of the cylinder, where the rod comes out, is called the rod end. The other end is called the cap end. This drawing shows two important areas of the cylinder. They are the lip seals on the piston and the rod gland seals here around the rod. For proper operation of a pneumatic cylinder, a positive seal must exist at both of these points. Their purpose is to prevent air from leaking. If leakage occurs, the cylinder won't develop its full rated output, and system efficiency will be reduced. Here are some types of resilient piston seals that you may see: an O-ring, a lip seal, and a leather cup. Resilient seals won't leak under most operating conditions, but they are less durable than either metallic or non-metallic piston rings, so they have to be replaced more frequently. Rod gland seals are used to provide an airtight fit where the rod comes out of the cylinder. They come in many sizes and are generally made from a resilient material. Here are some examples of rod gland seals. This one is a popular type. It is a lip type. The edge of the lip contacts the cylinder rod continuously and provides a good tight seal at low static and dynamic forces. Rod gland seals consist of a primary seal and a wiper seal. The primary seal keeps air and oil inside the cylinder. The wiper seal cleans the rod as it retracts. Now, in some applications, you may need to adjust the stroke of the cylinder. Here's one way it can be done. We can adjust the stroke with this threaded rod that's located in the cap end of the cylinder. It can be screwed in or out as necessary and serves as a stop for the piston when it retracts. Since cylinders can develop large forces and must be able to be mounted in a variety of industrial applications, you should be familiar with different mounting methods. So let's take a look at some of the more common types of mountings. This one has a fixed clevis on the cap end. It is a flexible mounting and allows the cylinder to pivot. This one uses a head trunnion on the rod end, which is another type of movable mount. This one has a mounting flange, so it can be bolted into place. And this one has side lugs attached to the end caps. Both of these last styles would be okay where rigid or fixed cylinder mounting is required. No matter what type of system is used, though, you're going to hear two terms used quite frequently: thrust load and tension load, and you should be familiar with what they mean. When a cylinder is connected to a load, so work is done when the cylinder rod is extending or pushing on the load, as you see in this illustration, it's called a thrust or compressive load. If work is being done while the cylinder rod is pulling on the load, it's called a tension load. And it really doesn't matter how the cylinder is positioned. That is, it can be mounted vertically or horizontally. The meaning of the terms remains the same. Because industrial applications cover such a wide range, a number of different types of cylinders are used in system design. Let's look at some of the more common ones. This is a single-acting cylinder. It's called a single-acting cylinder because air pressure is applied to the movable element in only one direction, through this inlet port here. And this causes the piston rod to extend. A spring is used to return the piston assembly. This is called a single-action spring return cylinder because air pressure is applied in only one direction, here. And the force developed by this spring makes the rod retract. This vent hole is to allow air that's trapped behind the piston to escape as the piston moves. Here's what's called a ram cylinder. It's basically a single-acting cylinder because there is only an inlet port here, but you can see that in this case the movable element is the piston rod itself. Gravity, or some other external force, returns the piston. This is a double-acting cylinder. It has two inlet ports, here and here, so that air pressure may be applied to drive the piston assembly in either direction. This is a single rod unit because the piston rod extends from only one end. If we make a cylinder with two rods connected to the piston, we have this type of actuator. It's called a double rod cylinder. With this type of unit, we can design systems with mechanical linkages connected to both ends. And depending upon our circuit requirements, the rods can be of different diameters to handle different sized loads. Well, you can see there are many types and styles of cylinders, and they can be used to cover a wide range of system applications. Not only is it necessary to select the right type of cylinder to do the job, but it must also be of the proper size. So let's examine what's involved in sizing a cylinder. First, we have to know certain things about the load. Not only the size of the basic load to be moved, but also what kinds of forces are needed to accelerate the load and to overcome any system friction. When the total load has been determined, including the weight of the piston rod, we can calculate the cylinder size using Pascal's law. We covered it in Lesson 2. Do you remember what it was? Here is the relationship. It tells us that the force developed by a cylinder is equal to the system air pressure times the cross-sectional area of the piston. And remember, the units have to be right. So if you want to get force in pounds, pressure must be expressed in pounds per square inch, and the area must be in square inches. Now let's see what this means when we look at an actual pneumatic cylinder. The first thing we have to do is to define a few terms. We're going to have to use two pressures. The one at the cap end of the cylinder we'll call P sub C, and the one at the rod end we'll call P sub R. And here are some important areas. This one here on the cap end is really the total area of the piston and the seal, so we'll call it A sub P. This small area is the area of the rod, and we'll label it A sub R. If we subtract the rod area from the area of the whole piston, we get the remainder, and it's called A sub E. The E stands for effective area, and it's here on the rod side of the piston. Depending upon the application, a cylinder may be driving either a thrust load, that's one where the cylinder is doing work when the rod extends, or a tension load, where the cylinder does work when the rod retracts. Here is the relationship to use for a thrust load. The compressive force that must be delivered by the cylinder we've labeled F sub C. The C stands for compression, because the rod is actually being compressed as the cylinder does work. The compressive force equals the pressure on the cap end times the total piston area. In those cases where we have a back pressure, as will be the case when there is a flow control valve in the exhaust line, our formula now becomes F sub C equals P sub C times A sub P minus P sub R times A sub E. And we subtract the pressure at the rod end times the effective area. However, under most conditions, the back pressure is assumed to be 0, and the formula once again becomes F sub C equals P sub C times A sub P. Okay, we said we were going to show how to select the right size cylinder for a certain load. So let's do an example to put this relationship to work. Here's the application. We want to push a load of 250 pounds, and our shop air supply is 100 pounds per square inch. Back to our equation. First, since our load is 250 pounds, the force of compression, F sub C, is the 250 pounds. How about air pressure? Well, although our shop air supply is 100 psi, we will use a value less than that. That is, we'll assume a case where there has been some heavy loading on the plant system, and it's dropped the supply to, say, 50 psi. If we use this value, we can be sure that under the worst case, the cylinder we select will be able to move the load. So we substitute 250 pounds for our load, F sub C, and 50 psi for P sub C, the pressure at the cap end of the cylinder. Now the pressure exhausting from the cylinder at the rod end will be very, very low. So low, in fact, that we can assume that it is 0. So as we said a minute ago, this part of the formula drops out. And we find that the piston to do this job must have an area of 5 square inches. Now remember our formula for finding the area of a circle? If we rearrange it like this, substitute our area, 5 square inches, here, and do the math, we see that our piston must have a diameter of at least 2.52 inches. Many manufacturers provide cylinder sizing charts in terms of cross-section area. This makes the selection job easier because it isn't necessary to calculate the diameter as we've just done. Just remember to select the smallest standard size piston to do the job. In our example, with a required diameter of at least 2.52 inches, a standard cylinder size of 3.25 inches is called for. But look at the area of the 2.5-inch cylinder. It is very nearly the 5 square inches that we need. In fact, we are so close to being able to use a 2.5-inch cylinder that it is the one we'd probably choose. It will move our load at a pressure of 51 psi. The example we've just shown was for determining the size of a cylinder when there is a thrust load. How about a situation where we have a tension load? Well, we can still use Pascal's law just as we did before. As you can see, we've rearranged a few terms, and this is the equation. F sub T is the force that the cylinder must supply during retraction to move the load, and it equals the pressure on the rod side, P sub R, times the effective area on the rod side, A sub E, minus any force on the piston side, P sub C, times the piston area, A sub P. And we can simplify this relationship. How? Well, since we are allowing air to exhaust freely from the cap end, the pressure at the cap end would be very, very small. We can, in fact, assume it is zero. So we can ignore that part of the equation. And here is our final equation, rearranged for effective area. It tells us that the effective area, A sub E, will be equal to the tension load, F sub T, divided by the pressure at the rod end, P sub R. Suppose we wanted to lift a 1-ton load and had a working pressure of 50 psi. The tension force would be 2,000 pounds, and the pressure here would be 50 psi. Using our simplified equation, we would divide the force or load, 2,000 pounds, by the pressure, 50 psi, and see that we'd need a cylinder with an effective area of 40 square inches. Now, piston rods come in various diameters, and we'll go into how to size a rod in Part 2 of Lesson 7. But for now, let's assume that a 1 3/8-inch rod is required here. So how large a piston would we require to get an effective area of 40 square inches on the rod end? Well, first we determine that the area of the rod is approximately 1.5 square inches. Then we take our formula for effective area and rearrange it like this. Now, our effective area must be 40 square inches, and the area of our rod is approximately 1.5 square inches. So the area of our piston will have to be at least 41.5 square inches. And as you'd find out from a manufacturer's chart, the smallest standard cylinder available to do the job will have an 8-inch bore. Okay, there are 3 more important things you should know about a cylinder when you are repairing or replacing one. First, as I mentioned a minute ago, rods come in various diameters. The size used depends on the particular load situation. Sometimes rod diameter can be very critical, and if a rod is too small for the job, it can actually buckle. So when you are replacing a cylinder, it's important to be sure that the new one has a rod with the same diameter as the one you're replacing. Second, when you open up a cylinder, you'll sometimes find one of these. It's called a stop tube, and as you can see, it is a metal collar, and when it's in place, it fits right here over the piston rod. Let's see why it's sometimes needed. What happens when a cylinder is driving a load that is unsupported? Well, there are stresses placed on the piston and cylinder. The weight pushing down out here creates an upward stress in here, and the rod gland here can have so much side loading force placed on it that it can wear out very quickly. Sometimes, even when the load itself is supported, the weight of just the rod can be enough to do damage to the cylinder or rod gland. Here is an exaggeration of what the piston rod looks like when a long-stroke cylinder is fully extended. You can see how the rod sags because of its own weight. In fact, a 5/8 inch diameter piston rod weighs about 1 pound per foot. If we had a rod of this size, 10 feet long, it would sag over 1 inch at the center. And this would produce a large side loading force on the rod gland, which would cause excessive wear and eventually leakage at the rod end. When it is in place and the piston rod is fully extended, as you see here, the stop tube separates the rod gland bushing and the piston. And this separation reduces greatly the amount of side loading force. To work effectively, the stop tube must be the proper length. If you are replacing a cylinder that has a stop tube in it, be sure that the new one has a stop tube of the same length. And last, before we leave cylinders, let's talk about the cushions that are sometimes built in. When a moving piston is suddenly stopped at the end of a stroke, a concussion results, which we call shock. If the piston is moving very rapidly and is stopped too abruptly, the shock can damage the cylinder. So to help protect the cylinder, manufacturers often equip them with cushions that help absorb the energy of the moving system. Here is a piston from a cylinder that is cushioned. This plug here on the cap side of the piston is called the cushion spear. This one here on the rod end is called a cushion sleeve. Here is a cylinder that has an adjustable cushion. Here are the inlet and outlet ports. Here is the rod, and you can see these adjusting screws near the cap and also here at the rod end. Some cylinders may only have cushioning on one end. Here's how a cushion works. Let's assume the cylinder is retracting and the cushion spear moves toward this seat at the cap end. As the cushion seats, it traps air here between the piston and the cap end. This air pressure helps slow the piston, and by adjusting this needle valve, we can affect the rate at which air bleeds off, and therefore the rate at which the cylinder cushions the load. There is quite a bit more to know about cushions, as well as about other design considerations of cylinders, but we'll save that for part 2 of this lesson. For now, let's talk about another kind of actuator, the pneumatic motor. Pneumatic motors are used in many applications that require rotary motion. They convert the potential energy of compressed air into rotary mechanical energy. This is just the reverse of what a compressor does. And if you'll think back to Lesson 5, you'll see that each type of pneumatic motor looks inside a lot like one of the compressors we discussed. There is a piston type, a vane motor, and a turbine, which is a lot like a dynamic compressor. These motors all have one thing in common. That is, when they are connected to a supply of air, they all develop an output torque. Torque is a rotary or turning effect. The torque rating of a motor tells us how much rotary force a motor can develop. In this illustration, if the motor produced a force of 50 pounds at a distance of 10 inches from the center of the shaft, we'd say the motor was producing a torque of 500 inch-pounds. Now, before we go any further, let me give you a safety tip. Unlike an electric motor, a pneumatic motor won't overload, but it can run away if the governor sticks. This can be dangerous, especially in grinding applications. So the built-in governor should be checked regularly to make sure it is operative. Here is an efficient pneumatic motor. It is a piston type. Here is the input port, and here is the exhaust port. Torque is delivered at the output shaft here. Compressed air comes in here and flows through these internal passages to the cylinders. The air pressure forces against the piston, causing it to move downward. The pistons are connected to the output shaft by these crankshafts, and an output torque is developed. This rotary valve here controls airflow to the proper cylinders. Piston-type motors generally run at speeds below 1,000 RPM. Since the price-to-power ratio of this type motor is quite high, they are not used as much as other types, like the vane motor. This is a vane-type motor. Here is the input port, and here is the exhaust port. Power is delivered at the output shaft here. The vane-type motor develops output torque by allowing compressed air to expand against extended vanes. Here is what the vane motor looks like inside. These movable vanes are free to move in this rotor, and when they are turning, form tight seals with the motor body here. As the rotor turns, power is delivered to this output shaft. The flow of air to the motor is directed by openings here in the port plate. Because the rotor is positioned off-center with respect to the ring, the area of the vanes exposed to air pressure increases as we go from bottom to top. This results in unequal pressure and results in a force being developed at the motor shaft. For the vane motor to operate efficiently, a positive seal must exist here at the vane tip. To assure this, the vanes are extended continuously by air pressure, directed to the underside of the vanes. During startup, light springs help ensure an initial seal until the motor comes up to speed. As you might suspect, the larger the area of the vanes, or the higher the air pressure that is applied to the motor, the more torque can be developed at the output shaft. Vane motors can produce about 10 times as much power in the same size as the piston type. The motor powering this high-speed grinder is a turbine motor. Turbine motors have a higher power-to-weight ratio than either the piston or vane type. But because they run at such a high speed, they are hard to gear down. When a designer selects a pneumatic motor for an application, he should take into account the starting and running speed, the torque required to start and drive the load, and the motor horsepower. A good rule of thumb for horsepower is that the air motor should deliver the required horsepower at about 65% of the available line pressure. That way you can be sure that the full line pressure will be enough for starting and for overloads. Well, this concludes Lesson 7, Part 1 of Parker Hannafin's Industrial Pneumatic Technology. I'm Dave Brown for Teletrain.